Welcome to video 4 of the mechanical power transmission. I think I lied to you from the last video. This will be the last video. Okay, I wanted to begin by talking about other types of reductions. So, we got more than just gears. We can have chains and sprockets, and we can have pulleys. So, for this first one, we have a chain and sprocket. And what's really, really cool about this is, once again, we can use the number of teeth to do our calculations. So let's say that this is our input side and this is our output side. The mechanical advantage of the system, output over input, would be 30 divided by 12, which is 2.5. So we would see the speed drop by a factor of 2.5, and we would see the torque increase by a factor of 2.5. Pulleys, well, pulleys don't have any teeth. So instead, use their diameters. So let's say that this is our input and our output. The mechanical advantage would equal 45 millimeters divided by 25 millimeters, which equals 1.8. So now, if you have a lawnmower that you're working on, you can go through and you can calculate the mechanical advantage to each one of your blades because those work off of pulley systems. Also, underneath the hood of your car, it also uses a pulley system as well. Now I said diameter, but you could use radius also if you wanted to. That would work. So radius or diameter, just as long as you're consistent. If you use one, stick with it. Okay, let's start throwing this all together now. And let's start doing a larger problem. So here's what we have. We have an arm with a 30 Newton weight attached to it, and the arm itself is 0.5 meters long. We are using one VEX 393 motor. Now this is way too much torque for a single motor. So what we want to do is we want to use a gear system. And we want to figure out what gear ratio we would need so that single motor can do this task. Now, the characteristics of a 393 motor, just in case you forgot, it has a free speed of 100 RPMs. The stall torque is 1.67 Newton meters. It has a stall current of 4.8 amps and a free current of 0.37 amps. So let's go ahead and start with the math. Let's begin by figuring out how much torque is needed. So this is going to be F times R. The theta is going to equal 90s, and sine of 90 is 1. So this is going to be 30 newtons times 0.5 meters. That obviously gives us 15 Newton meters. So as you can see, this clearly is not enough torque to lift this mass. Our input torque is 1.67 Newton meters. Well, remember that the output torque also equals the input torque times mechanical advantage. So that means if I take the output torque divided by the input torque, that'll give me the mechanical advantage that I need. So this mechanical advantage then would equal 15 Newton meters divided by 1.67 Newton meters. And that gives me a mechanical advantage of 8.98. I might as well go ahead and round that up to, I need a mechanical advantage of 9. So how do I get that? In the VEX system, the largest we have for a non-compound is a 12 to 84. So we're going to need something a little more. If I have a mechanical advantage of an 84 to a 12, 7 is as big as I can get. I need 9, and I can only get 7 with a single 84 and a single 12. So obviously I need to go to a compound system. So with this compound system, be looking at the different lists, I think what would help out, or what would work nicely, is if I did a 12 to an 84, and then in the compound did a 36 to a 60. If I worked out that math, the mechanical advantage gives me 84 over 12 times 60 over 36, and that comes out to about 11.7. So it gives me above the 9 with a little extra breathing room. And this, ladies and gentlemen, finishes up our notes on the mechanical power transmission. Ciao.